Okay, in this video, we're going to talk about current and resistance. And hopefully you've just watched the previous video on voltage. And so we're going to start with our idea of voltage and then work towards these two. So again, in the last video, I talked about how a battery, what it does is it will create a negative region and a positive region, an area with an excess of electrons, in an area with a deficit of electrons. This one would be negative, this one would be positive. And what that does, because like charges repel and unlike charges attract, is it means that these electrons would like to move from here to here. Current is a measure of how many of those electrons are actually flowing from one section to the other section in 1 second. So current, for some reason we use the symbol I for current, is the amount of charge, Q, divided by the amount of time. So as these electrons start to move from one location to the next, how many electrons flow? The actual amount of electrons that we have moving from one location to another location depends on two factors. First of all, when these two regions are set up at the positive and negative terminals of the battery, we can have regions that are more negative and more positive, or less negative and less positive. So the more negative this is, and the more positive this is, the bigger difference between these two. Sometimes this is called a potential difference, or that's what we call voltage. The more electrons will want to flow from one to the other. So again, more positive, more negative means more potential difference, or more voltage, we say. And so that's more energy for moving around. And so basically that means they want to move really, really badly around the circuit. And so if they want to go really fast, that will make the current go up. So as voltage goes up, current goes up. That's not the only factor though. Again, for these things to flow from one location to another location, we need a pathway. And usually in that pathway, so that we can make use of the flow of these electrons, we put in some sort of electrical load. Or some sort of resistance. So what that means then is when these electrons try to get away from this negative region and get over to this positive region, they get stuck going through some sort of material that uses their energy. As they flow past. So this could be like a light bulb, this could be like a speaker. It's some sort of thing that's going to convert this electrical energy into some other useful form of energy. And as a result, it's also going to restrict the flow of electrons from one location to another location. So we get this big buildup of electrons that are trying to get through here, and then we have this small resistance region. And then as a result, we don't have as many electrons here, and that's what maintains our potential difference. This can be thought of a lot like a traffic jam, where maybe there's a lot of people that live outside of the city and they want to get into the city, and then there's certain regions along the road where the road naturally narrows, or where two roads come together, or something like that, and you get a buildup of cars before it and not very many cars after it, and that difference, that potential difference, means that electrons really want to get through there. And So since they really want to get through there, when they do get there, that resistance or that load can use their electrical energy in hopefully some other useful way. The narrower this is, or the more resistive this is, the higher the resistance, the harder it is for electrons to flow. So what that means is as the resistance goes up, the current, or the actual flow of electrons, has to go down. So we have these two basic factors that are going to affect how many electrons are able to flow around the circuit. We can summarize them both in one equation. I is directly proportional to voltage. As the voltage goes up, the current goes up. And it's inversely proportional to resistance. As the resistance gets higher, the actual flow of electrons gets lower. This is called Ohm's law. And this way of writing it is fine, but it's more commonly written as V equals IR, where they've just brought the R up to this side here. So that is the common way that Ohm's law is written. I like this way better because it helps us understand that voltage and resistance are what are coming together to dictate how much current can flow. The more the electrons want to get around the circuit, the more of them go. The harder it is, or the more resistance there is in the circuit, the less of them that flow. While we're here, this is a useful time to talk about what kinds of structures in an electric circuit might make resistance and what would make the resistance higher or lower. Here we're going to talk about two factors, material factors and geometry factors. To make electrically resistive material, we can use insulators or semiconductors. Different carbon compounds, like graphite, are good semiconductors and serve as good materials for resistors. But also, the filament in a light bulb, for example, would be acting as a resistor. So the second way we can make a resistor is by looking at its geometry. We can look at its area and its length. So if we imagine in three-dimensional space that the resistor has some cross-sectional area, the bigger the area, the more room for electrons to get through. The lower the resistance. Right? So if it's a nice, big, and wide highway, 4 lanes, it's not going to provide very much resistance. But if you narrow it down, you reduce its cross-sectional area down to just 1 lane, then you might find that you've got a lot of resistance in your highway. Also, again, with our nice real 3-dimensional resistor here, that resistor has some length. I think of this as how long that traffic interruption happens for. Here, the longer the resistor, the more resistance, or the harder it is. And that makes a higher resistance. Again, imagining our analogy to the cars driving down the highway, if the road is reduced to 1 lane, the longer you're stuck going in that 1 lane situation, the more traffic you're going to create, the more resistance to electron flow that you're going to have. So as you make your resistor longer, that's like creating a longer region where the electrons have a restricted ability to flow. So again, one more time, current is the actual number of electrons or the actual amount of charge that's moving around the circuit. The more difference or the more voltage we have, or the more different the negative and positive parts created by the battery are, the more electrons want to flow, the more current we'll get. So voltage and current are directly related to each other. The more resistance, or the narrower this small little region is, the harder it is for electrons to flow. So as the resistance goes up, the current goes down. We can summarize those all in Ohm's law. And if we use semiconductor materials and control their cross-sectional area and their length, we can control how much resistance we get. The wider the semiconductor, the lower the resistance, the more area there is for electrons to flow. The longer the blockage, the harder it is for electrons to go, and as a result, the higher resistance.